Welcome to the last before spring break session of the Rutgers University Experimental Math Seminar. Today's speaker is Jay Pantone, who will speak about combinatorial exploration. As usual, you are welcome to unmute yourself anytime, ask a question, and then mute yourself back. Thank you.
Yeah, and let me reiterate, please do interrupt me if you have questions. I'm happy to take them at any time. My spring break is also next week, so I'm glad we could celebrate that together here. Okay, so combinatorial exploration is a project that I've been working on with a bunch of co-authors who you see here on the right-hand side, including Henning, who has joined us. It's been about 5 years of work, and finally we have a paper on the archive just as of a couple weeks ago. So if you're more curious about any of this, you are very welcome to go look at that. And I also wanted to take the chance to point out that there have been a huge number of undergraduate and graduate students who have done bachelor's and master's projects kind of in this area as well. So here's a big list of them, mostly working with Henning, or maybe I think all of them working with Henning and Christian Bean. And so I wanted to take the chance to acknowledge them as well. So in this talk, when I use the phrase combinatorial family, all I mean by that is some set of objects defined by some property. So a very vague definition, but I mean things like, for example, walks in the plane that never collide with themselves, or permutations whose entries never form certain patterns, or polyominoes whose columns are all convex. So just the thing we're all familiar with, sets of objects with some collective property. And as an enumerative combinatorialist, I ask questions along the lines of how many are there of each size? Of course, we know there are tons of different kinds of answers you can get to that question. You can ask, how does the counting sequence grow as n goes to infinity? You can ask about random sampling. Is there a quick way that I can sample an object uniformly at random of a certain size? And lastly, let me give a more structurally minded question. How can we build the objects of size n out of the objects of a smaller size? So that's more about how the objects relate to each other. And so when we're exploring questions like this, I like to think about the workflow of enumerative combinatorics. This is how I think about it in my head. And the first step for me is always to try to find some kind of structural description of the combinatorial family. Another vague phrase here, but all I mean is that if you want to start learning about a set of objects, you have to have some initial idea. You have to have some way of talking about objects in terms of other objects to kind of get you started. Once you have some kind of structural information, then usually you try to do something like convert it into a generating function. And there's a nice toolkit for doing this called symbolic combinatorics. I'm not saying that it always works or that it's easy or anything, but there's at least a bunch of tools that can help you do this. And then once you have a generating function, well, we apply the tools of analytic combinatorics to try to learn about other things like, for example, asymptotic growth. So once again, there's a toolkit that can take you from a generating function to many other things that you might want to learn about. But for me personally, I always find this first step to be the hard part. Now, big caveat, different parts for different problems for different people are all the hard part. But for me personally, that's where I struggle the most, is you have to have some kind of idea out of nowhere to be able to describe the structure of some set of objects. Okay, so let me give a very trivial example of what I mean by this workflow of enumerative combinatorics. I'm going to define a very simple set of objects, up-down walks. These will be walks in the plane that start at the origin over here, and they take steps northeast and southeast. So they go up and they go down. There's no restrictions about staying above the axis, no restrictions about ending at the axis, just walks that go up and down. The size of one of these walks will be the number of steps it takes. So here's an up-down walk of size 20. Now, of course, we all know how many of these there are of size n, but let's pretend for a moment that we didn't and try to go through some of these steps of the workflow. Before we answer how many there are, we need some way of understanding the structure of the class. So here is, in English, in words, one way that you might describe the structure of this set of objects. You could say the set of up-down walks of size n can be built by appending either an up step or a down step to every up-down walk of size 1 less. Okay, so pretty simple. You take any walk of size 1 shorter, you're allowed to go up, you're allowed to go down because we have no restrictions. And so we get all walks of size n. We also have a base case that we should probably mention where there's a single walk of size 0. And those two pieces of information together are enough to understand this whole set of objects. But what I want to do is write this structural information in a tree-like format that's going to be, well, not completely formal yet, but at least a little bit more formal than this English description. So let me define W to be the set of these up-down walks. And let me show you a picture that doesn't mean anything to you yet, but that I'm going to try to explain. So here I have a tree. I've got a bunch of vertices. Each vertex is labeled by a set. So this root of this tree here is labeled by this set W, the set of all up-down walks. And some of these vertices down here are also labeled by W. Then I have this vertex, this W sub up arrow. This means all of the walks in W that end in an up step. This means over here, the subset of walks in W that end in a down step. Okay, over here, this represents the single walk of length 0, the single walk of length 1 that goes up, and the single walk of length 1 that goes down. So again, the tree doesn't mean anything yet, but for now, the vertices are all labeled by sets. Now here is where I try to explain the meaning of the tree. Every time we have a parent vertex with some children, that represents some kind of structural information about representing the parent in terms of the children. So this first one, for example, this relationship between this parent vertex and these 3 children. This is a disjoint union type of rule. It tells us every walk is either the empty walk, or it ends in an up step, or it ends in a down step. So this relationship is telling us the parent is the disjoint union of these 3 children. It's a piece of structural information from the parent to the children. Now that's not true with this relationship here. It's not true that walks that end in an up step are the union of all walks and an up step. It's actually a different kind of relationship. It's more of a concatenation kind of thing. This rule here represents the fact that the walks that end in an up step, this set here, you can think of as the concatenation of any walk plus an up arrow. And similarly, every walk that ends in a down step, you could think of as the concatenation of any walk plus a down step. So in some sense, we have decomposed this root set into these 3 children as a disjoint union kind of relationship. We've decomposed this vertex into 2 children as a concatenation kind of relationship, and the same for over here. So this is a tree-like structure that is kind of informally representing that structural description that we had in words on the last slide. Now, what I want to show you is from this structural description, we can learn the kinds of things we want to in enumerative combinatorics. So here's the same picture on the right-hand side where I've labeled the vertices according to their sets. From this tree, we can derive a system of equations for the generating functions.
Let me just interrupt for historical accuracy. This is
Please.
really the so-called Berger approach of a grammatical approach of thinking of it linguistically as a grammar.
It is, and in a slide or two, I'm going to tell you that these are really combinatorial specifications, and go from there. These are really just pictorial versions of that. So yes, thank you. This vertex, this root, we said A is the disjoint union of B, C, and D. So in terms of their generating functions, that corresponds to the sum of the generating functions. B consists of the single walk of size 0, so its generating function is 1. C is a concatenation, so that corresponds to the product of generating functions, and the same is true for D. And lastly, these sets E and F, these are each just a single walk of size 1, so they have a generating function of just X. So directly from this structural information, we get a system of equations for the generating functions that, of course, we can solve and get the generating function and the counting sequence that we all knew was the answer to this, that there are 2 to the n walks of size n. I could have done the same thing instead of generating functions. I could have gotten a bunch of formulas for counting sequences directly, but I didn't do that because I wanted to save some time. Now, these trees that I'm drawing, they're really just pictorial ways to think about something called a combinatorial specification that have been around for a long time. Here is the combinatorial specification that this tree represents, and I'll explain what I mean by this. Every time we have a parent associated to some children, that corresponds to a combinatorial rule. A rule is a parent on the left pointing to some children on the right. Whenever we have a vertex that's just a finite set, like B, E, and F, we write that as just the set's name on the left and the actual finite set on the right-hand side. So we have from this tree a list of 6 combinatorial rules. What makes a set of rules a specification is a very certain property. It's the property that every symbol on the right-hand side, that means the A through F, every symbol on the right-hand side appears on exactly one left-hand side. So if you have a set of rules with that property, it's called a specification. In general, having a combinatorial specification means that you have a full description of the class, you have enough structural understanding to learn things like counting sequences and all that stuff. It is possible for a specification to be trivial and not really give you any information. But if it's not trivial, it means in some sense you've won the game, you have all the information that you want. So this example was very trivial and very easy, but I want to show you that it gets a little bit tricky even if you make the problem just slightly more difficult. So suppose that I wanted to understand the set, which I'll call F, of walks that don't go up 3 times in a row. So that's the only restriction. You don't go up 3 times in a row. And what I've drawn here is the exact same tree, but with all of the W's turned into F's. And now this tree is not true anymore. The first part is still true. All walks in my set F are the disjoint union of the walk of size 0, the walks in F that end in an upstep, and the walks in F that end in a downstep. That disjoint union is still definitely true. But now this rule is false. It's no longer true that the set of my walks in F that happen to end in an upstep, I can't form that set by taking all walks and appending an upstep, because I'll make some things that aren't allowed. For example, F has plenty of walks that end by going up 2 times in a row, and then I can't append a 3rd upstep because that will break my set. So this rule is broken. This other one, as it turns out, is okay, but obviously we don't have a full description. So I guarantee that anybody here in this talk could spend 3 or 4 minutes trying to fix the tree by adding another rule or 2, and you would be able to do it. But if you're like me, you might make a mistake or 2 first before you get it exactly right. And so this is what I'm trying to illustrate as the first step in the workflow being kind of tricky. When you want to find some structure like this, you need usually some kind of experience, you have some trial and error, you have to call upon your intuition, and probably bang your head against the wall a couple times before you get things correct. So jumping back here, this first step of finding the structural description, the part that I find is the hard part, that's the focus of combinatorial exploration. What combinatorial exploration does is it teaches the computer how to automate that part of the process. Now, this is where I really want to emphasize that these methods, combinatorial exploration, is experimental in the sense that when you hit go on this algorithm, when you type in your command and you hit enter, you don't know ahead of time if it's going to finish or not. It might finish and give you an answer, or it might run forever until you run out of patience or memory. But it's fully rigorous in the sense that if you get an answer, it is rigorously proved and verified. So it's not experimental in that sense. And that's what I like about it, is when you get an answer, it's a proof. Okay, so suppose that you have some sets that you want to learn about, and you want to use combinatorial exploration. Before I tell you what the process actually is, I'll tell you what you would need to have to get started. The first thing that you need to know ahead of time is some domain of objects that you want to try to enumerate. So up-down walks, for example, or permutations or polyominoes or whatever. You have to decide which set of objects you're going to be worried about for the moment. And then you need some way to represent subsets of those objects in a finite way. So for example, if we're working with up-down walks, maybe avoiding some kind of patterns or not, you're not going to be able to store in the computer all subsets of walks. Those are mostly infinite sets, and you're not going to be able to store them. So you have to decide which sets you do want to store. The example that we had is we had a subset like W up arrow. Those are all the ones with a suffix, which is up. So you might decide, I want to store all of the subsets where I give it a fixed suffix, or maybe a fixed prefix, or maybe both. And those are the subsets that you're going to allow the computer to work with. The last thing you need, and probably the most important one, is some small set of decomposition strategies that you hope will break your sets into simpler sets. So in the last example, that was things like a disjoint union strategy that broke one vertex into 3 children, or concatenation strategies that split some of our vertices into 2 children. And so you have to decide on some decomposition strategies. Now, the one thing I really want to emphasize here is that you are deciding these strategies with some entire domain in mind. You're not thinking specifically about, I want to enumerate one set. You're thinking about, if I wanted to enumerate a bunch of sets that involve up-down walks, what kinds of strategies would tend to be useful there? Once you develop those, though, then you apply them to all of those subsets of the domain that you want to learn about. So just to give a quick example of what I mean, we'll talk in a little bit about the field of permutation patterns, which was our inspiration for doing this. We developed strategies that work in general when you're trying to enumerate what we call permutation classes. So we didn't necessarily focus on one particular class, we just developed general strategies. Then you take those and you apply them to all of the different permutation classes you want to enumerate and hope that they combine in a nice way to give you an answer. Okay, so now it's time to actually tell you what combinatorial exploration is and how it works. Suppose that we have some set A that we want to enumerate, up-down walks, avoiding some pattern, or some kind of permutation class, whatever. It's some set that we want to enumerate. And we've already decided ahead of time on some decomposition strategies that we know will work in this domain. We hope that it will take some sets and split them up into simpler sets. So let's imagine for the moment that we have 5 decomposition strategies that we've thought of and that we've implemented into our algorithm. We take those 5 and we try to apply them to this root set. And we hope that it might split them into some simpler sets. So let's say that the first decomposition strategy applies, and it says, aha, I can tell you that I can break the set A into some children B and C. And what this means is that if I understand B and C fully, I can use that information to understand A fully. Now we try to apply our second decomposition strategy, and maybe it says, oh, I don't work here. I don't apply to the set A. I can't tell you any information. Then we try the third one, and maybe it tells us, well, I know how to break up A into some other sets. Maybe the fourth one also breaks up some information. And let's say the fifth one just doesn't apply at all. So at this point, what we've done is we've thought about, or we've discovered 3 different ways to split A into some children. Now, it's possible that you actually split it into 3 or 4 or 5 here, or that some of these sets are actually the same set. I'm just kind of showing you a generic version of the picture. Okay, so we have these 6 new sets that we've discovered, B through G. What we do now is we take our 5 decomposition strategies again, we apply them to each of these 6. So we apply all 5 of them to B. Maybe one of them says I can split B into H and I, and another one says I can split it into J and K, and maybe the other 3 don't apply at all. Maybe none of the 5 apply to C. And let's say, just for example, 2 of them, or one of them applies to D, 2 of them apply to E, none of them to F, and 1 to G. So we've taken our 5 strategies and applied them to all 6 sets. You can probably guess what we do next. We take our 5 strategies, we apply them to all of these new things that we've discovered. It feels like we're going to get such a combinatorial explosion that surely we can't do anything useful. But it turns out that you can do a lot of things in practice to mitigate the combinatorial explosion, and you can actually have a lot of success. So what we've done is we're kind of exploring this universe of sets by breaking parents into children. This complicated picture I'm showing you is really just a pictorial version of a big list of combinatorial rules. So when one of our strategies discovers that the set A could be broken down into B and C, that's like saying, I know the combinatorial rule A going to BC makes sense. And so does A to DE, and A to FG, B to HI, and so on. So as you're running combinatorial exploration, you're discovering.
Jay, I'm a little bit
Yes.
confused. So as is mutually exclusive?
Not
Once you know how to decompose A into B and C, why do you need D and E? I don't understand.
Okay, if you give me 1 second, I think I can answer your question.
Okay.
So what you want to find is a combinatorial specification. And a giant list of rules is not necessarily a specification. If you have sometimes we'll have 100 million rules when we do this in practice. And if it's not a specification, you haven't won the game yet. You need a full combinatorial specification to be able to be sure that whatever system of equations you might write down for the generating function, for example, actually has a unique solution. So the reason that you have to...
Are they mutually exclusive, B and C, D, E?
And so not necessarily. It might be the case that the set B is also equal to the set D, for example, or maybe E equals G. And sometimes maybe L equals A again. Just like if we think back to that example.
Assuming that A is a disjoint union of subset of A is handled by B and C, another subset by D and E.
So that depends on what strategies you've implemented. So for example, one of these might have discovered that A is the disjoint union of B and C. Another one might have discovered that A is the concatenation of D and E, for whatever that might mean for the objects in question. You might have A going to just F. You could have a rule that only has one child. That might be something like, if you take F and you do this complicated thing to it, you can reconstruct A. So it's discovering a lot of isolated rules about these sets over time. But so far, that doesn't guarantee that we will be able to enumerate the root A, which is our actual goal.
Or you keep your options open. You don't know which of them will work.
Exactly. We don't know which combination of rules is going to give us success. So as we're running, we're building this huge list of rules. When that giant list of rules happens to contain a subset of rules that's a combinatorial specification, and it involves that root set, then you've won the game. You don't know ahead of time which one of these 3 you might need, or which one of these 6 you might need, and so on. But if this giant list of maybe 100 million rules ends up having a subset of 50 of them that make a specification, then you're golden and you've enumerated, or you can enumerate that root set.
Thank you.
So the thing you might wonder is, well, okay, how can you search a set of 100 million rules for a specification of size 50? Obviously, you can't check all the subsets of size 50. But this is one of the many little algorithms that we've developed along the way. It turns out that you can search a list of rules for a combinatorial specification in a fast polynomial way. So that turns out to not be an obstacle here. So this is the main idea of combinatorial exploration. We're building perpetually a giant list of structural rules that rigorously each rule must be true, because we're deriving it using something simple like a disjoint union. And if that giant list of rules happens to have a subset that's a combinatorial specification, then we've completed that first step in the workflow. We have found a structural description. So a couple caveats. Like I just said, this is the main idea. There's a lot of complicated stuff going on under the hood, a lot of little algorithms that we've had to develop to make sure that we can mitigate combinatorial explosion problems. We can recognize if 2 sets that look different at first might actually be the same set, and so on. And one thing I mentioned earlier is that it's possible to write down combinatorial specifications that are tautological, meaning you could write down a system of equations, but it's something like A equals B and B equals A. You don't learn anything from that system of equations. So we've had to set up a kind of big theoretical framework that guarantees that all of the specifications that we get are guaranteed to not be tautological. They're guaranteed to give you counting sequences and all that kind of stuff. So this is fully implemented in Python, and it's available on GitHub. We'll have the link in a second. Altogether, it's 31,000 lines of Python code. Now that's more than it sounds, or that's less than it sounds like, because a lot of this is various things like writing tests and stuff. But it was a big project that involved a lot of grad students and a lot of coding over many years. So suppose that you have some objects that you want to enumerate. the way that we wrote combinatorial exploration was with a focus on being domain agnostic. So the main routines that do all of this stuff that I described on the last slide, they don't assume that you're working with permutations or polyominoes or anything like that. They just assume you have some combinatorial set, and it doesn't make any other assumptions. So what you can do is write your own Python code to describe the objects that you want to do. So if you want to run this, you decide on how you want to represent your sets of objects in the computer, and you write some Python code to represent, for example, sets of walks with certain properties. You decide on which decomposition strategies you think will be good at splitting sets into simpler sets, and you code Python functions to do those. This is where it really helps to have some experience in the domain, because if you've read a lot of papers on permutation patterns, you probably have some generic feeling for what strategies tend to be useful when breaking down sets into smaller sets. So you implement these things, you feed them into our framework, and you hit go, and it will do all of this work for you. So I said on the last slide, it was something like 31,000 lines of code. The breakdown for that is the actual framework to run all of this is only about 7,000 lines of code. And if you look on the GitHub repository, there's a README page that gives you an example for implementing combinatorial exploration in the domain of binary words avoiding patterns. So that's a pretty trivial example. You can just make a little finite state machine and enumerate these. But we thought it was a good example for how you might implement your own domain using the framework. And so that's only about 200 lines of code for a simple representation of these sets and some simple decomposition strategies. The domain that we were very interested in, because this is most of our research areas and it kind of inspired the project, is permutation patterns. So now we spent a lot of time implementing our own framework with this domain. And so we spent a lot of time thinking about things like efficient representations of sets of permutations and things like that. And so it's about 24,000 lines of code to apply this framework to permutation patterns. So we have coded a couple of different domains. One of those domains is, like I said, permutation patterns. Another one is pattern avoiding set partitions. This was a project that, I forget if it was a master's student or I think it was some bachelor students, as well as pattern avoiding Motzkin paths. So Motzkin paths is another example of a domain that's fully solved. You can write down a context-free grammar to enumerate pattern avoiding Motzkin paths. But some undergraduates were able to come up with a representation and a couple strategies that can also do them all automatically. And I'll show you at the end of this talk, we've thought about some domains on paper. So we haven't implemented it, but it seems like we can do some examples of polyominoes with certain properties, inversion sequences, and alternating sign matrices. Now, I'm not claiming that we can enumerate all polyominoes. That's a big open problem. We can't. But we can do some example. Well, I'll show you when we get there, but we can do some examples with these domains. So let me talk a little bit about permutation patterns. I don't have time to define the whole field, but I'll try to give you just a little bit of a sense of the kinds of things people study. And I'll tell you what kind of success combinatorial exploration has in this domain. If you're given a set of permutations B, then you can study the set of permutations that avoid all of the permutations in B as patterns. So we have some notion of a bigger permutation containing a smaller one. And if you look at the ones that don't contain certain smaller ones, those sets are called permutation classes. One interesting case is when you think about permutation classes that must avoid two given patterns of length 4. So if you think about all the different combinations of two patterns of length 4, at first you might think there are 24 choose 2 different cases. And there are, but a lot of those are kind of trivially equivalent to each other because of some symmetries. Like if you reverse a permutation, then it reverses what it avoids, for example. So once you account for those different symmetries, there are essentially 56 different permutation classes that avoid two patterns of length 4. And there's actually a Wikipedia page that lists all 56 and references who's enumerated them. They are all known now, all 56 as of a couple of years ago, but it took several decades and dozens of papers and very different techniques. So these classes were kind of a proving ground for various techniques. Somebody might come up with a new way to enumerate permutation classes and say, oh, and look, it enumerates 2 new of these 56 ones. So that was kind of a role that they served for many years. And also the difficulty of these 56 ranges from, one of them is finite. A lot of them have rational generating functions. And it seems like 3 of them actually have non-definite, even non-differential algebraic generating functions. So they range from very easy to very difficult. So over time, yeah.
And what do you mean by solving them? A polynomial time algorithm? Because
well, that depends on the class. So for the 3 that are conjectured to be non-differential algebraic, this was some work I did with a couple other people on C machines. So for there, we just have a polynomial time algorithm. For all of the other 53, we have explicit algebraic or rational generating functions.
So by completely solved, you mean a polynomial time algorithm?
Yes.
Yeah. And are they all in the OIS? I bet they are, right? All the 56?
I bet they are. I think many of them were in the OAS before they were even solved with just the first 10 or so terms. I would guess they are all there, yeah.
And some of them are equal to each other. So how many different sequences are they?
I think 38 or something like that. I'm just pulling it from, I think you end up getting 38 different enumeration sequences.
Ah, thank you.
Yeah. So over time, as we were working on this project, we wanted combinatorial exploration to be able to reproduce as many of these as possible. And early on, we got a couple and then a couple more. By the end, though, combinatorial exploration can now do all 56 of these 56 classes. And by do, like to answer your question, I mean derive a rigorously proved combinatorial specification. In all of the cases where we know the final answer is algebraic, we can compute that algebraic generating function. And in the 3 remaining cases that are not algebraic and probably not definite, we have a polynomial time counting algorithm. So the thing I want to make really clear here is that the way we managed to enumerate all 56 of these, it was not by reading the 56 different papers or however many papers it was and copying whatever methods they used and implementing them in code. There are some really ad hoc methods to do some of those 56. And so I think that would be kind of cheating and not very interesting. We were able to do these 56 by coming up with a fairly small set of strategies. I don't know exactly how many we used overall, but probably something in the order of like 8 or 9. And taking those decomposition strategies together in lots of different combinations was enough to do all 56 of these. So in my opinion, it kind of puts all of these enumerations under one umbrella of a small set of techniques that was able to enumerate all of these classes. So if you know anything about permutation patterns, your question now is what can it do on the hardest class of all, which is avoiding 1 through 2, 4? Well, there are essentially 7 different ways to avoid a pattern of length 1 when you account for symmetries and stuff. And we can't do 1, 3, 2, 4 yet. We can do the other 6 though. And I think that is still pretty impressive. So some of those 6 have, we know they're counting sequences, but they've never been directly enumerated. For example, one of them was enumerated by finding that it was in bijection with some kind of tree with a certain property. That was done by Miklos Shpona. And then he enumerated the trees. Or maybe the trees were already enumerated. I can't quite remember. But we can provide the first ever direct enumeration of that particular class. While we can't do 1, 3, 2, 4 yet, we do have a couple new things in the pipeline. So I'm not going to say that I'm confident we can do it. But the way I like to think about this is if there even exists a polynomial time algorithm to count it, I think we will find it.
I hope that you don't, because otherwise I'm going to lose my bet.
I know, I'm sorry. I think Einar would make some money if we can do it. But I'll tell you what, if we can do it, I'll pay for your loss of the bet. That's how excited I would be.
Thank you.
Okay, so like I said, we can do 56 out of 56 avoiding 2 patterns. And as you avoid more patterns, really it becomes an easier problem. So we can do all of them avoiding 3 patterns. And in fact, we can do any number of patterns that you avoid of length length 4 up to all 24 of them. So all the different ways you could avoid any combination of length 4, except for avoiding this one, we can do automatically and rigorously. Now, we're not just reproving old results. We can reprove dozens of known results, but also dozens of new results. So plenty of either conjectures in the literature or classes that were relevant for some reason, but left unenumerated. We can find either generating functions or polynomial time algorithms for many of them. Also, what we can do is correct some wrong results in the literature. in a way that we can be confident of. So for example, there was a thesis that was something like 200 pages, and this was not the main result, but it was an important result, was the enumeration of a class. And somewhere along the way, there was one tiny little mistake, and so the final result was wrong. So this is one way that we can correct that and be quite sure of the result. Now, we have created, in addition to publishing this code, we've created a website that catalogs all of these results that we get for permutation patterns. This is very much inspired by the OAS, as well as Bridget Tenner's database of permutation classes, certainly not replacements for those. We call it PermPAL. That stands for the Permutation Pattern Avoidance Library. And if I have some time at the end, I'll show you, I'll actually go to it and click around and things. But it has this home page here where it shows you some of the notable successes that we've had. If you can like go to a random one, you can search for different ones. And if you go to a page for a particular class, so for example, avoiding 1342, it gives you the information that we have rigorously proved about it. So you can get the counting sequence. We show 15 terms, but we give you up to 100 terms for every class. And if you see a counting sequence and you wonder, is that on the OAS? You just click this little button and it brings you to the OAS automatically searching for these results. We give you the generating function when we are able to solve for it, a minimal polynomial when we have one, a recurrence that Maple has computed for us, and so on. We also show you up to 5 combinatorial specifications that we have. So if you scroll down, you would see it. This is just a screenshot, so you don't. And it was too big to put on the slide, but you can see the specifications. You can scroll down and see, for example, the system of equations that came out of our specification. I'm not going to linger on the system for too long because I will show you more systems of equations in a minute. But you can see, for example, we have a catalytic variable, which I know will interest some people here. Now, one very cool thing that you can do when you have a combinatorial specification is that you can sample from it uniformly at random. So here's a picture that I'm going to explain to you. One way that you could sample, let's say, a permutation of length 300 from a class, from a specific pattern avoiding set. What you want is to be guaranteed that you're sampling each permutation with equal probability. So the dumb way to do it would be to try to generate all of them of length 300, store them in some big set, and pick one. But of course, there's an astronomical number of them, and so you can never do that. So if you don't have some kind of structure, it's hard to sample and know that you're doing it uniformly at random. But if you have a combinatorial specification, you can do it. And since this is all implemented in code, we can do it easily. So this is a picture of what I call a heat map of a permutation class. This is one of those classes that avoids 2 patterns of length 4. I can't remember which one. But what we do is we sample 1 million permutations of length 300 from this set. And it's guaranteed to be uniformly at random. If you have one single permutation, you could imagine it as being shown by a bunch of dots in the plane. If, say, the first entry of the permutation is a 10, you put a dot at height 10. Say the next one is 100, you put a dot at height 100. The next one is a 1, you have a dot at height 1, and so on. So the way that we make these heat maps is we take 1 million permutations, we take all of their plots, and we kind of stack them on top of each other and make them mostly translucent. So when you see these regions that are very dark, like kind of right here, right below the diagonal, or especially here in the corners, that means that most of the permutations had entries in kind of that region of the picture. When you see a light one, like kind of right in the diagonal or these sides, that means very few permutations had entries there. So we can see some kind of general shape for this class. It has some entries below the diagonal, but not very spread out, and some entries above the diagonal that are more spread out. And so for, I think, probably the first time this has ever been done, we can sample all 56 of those 2x4s, for example, and get pictures for all of them. Now, I lied a little bit. This is only 55 pictures. One of those classes is finite, and the longest permutation it has is length, I don't know, 12 or something like that. So we can't sample permutations of length 300. But these are pictures for the other 55 classes. A lot of them are kind of boring. They're just diagonal lines with some kind of shading, but there are some real surprises here. I like this one that to me kind of looks like a football with the laces in the middle. We've got this one here. We've got these here. There's a class that looks like a diamond. That's kind of very crisp. And so for the first time, we can look at all these pictures and really have a sense of the differences between some permutation classes. These figures are also in the paper. So if you want to stare at them for longer like me, you can always go to the archive and find that page. The last thing I want to say about permutation patterns is just to highlight a couple of the difficulties that we run into computationally. If you look at permutations avoiding 1, 3, 2, we get a really simple system of equations that we can solve for the Catalan numbers. No big surprise there. But one of those 2x4s, the best we can do is a system of 550 algebraic equations, so sums and products. And no matter what I try in Maple, whether I try to solve directly or do elimination or do Grobner bases, I can't solve this system in Maple. And Maple's pretty good at these things. So I would be shocked if anything could solve it directly. If there is, I'd really want to know about it. So what we had to resort to, I know that Daron's going to love this, is a guess and check approach. From the specification, we can get counting algorithms, not just for the root, but actually for every set involved. So what we had to do in this case was generate 1,000 terms in the counting sequence for all 550 of these sets, and then guess algebraic generating functions for all 550 of them. And we really did need that many terms to do it. And then you can rigorously check that your guessed generating functions satisfy this system, and therefore they must be the correct answer. There's a lot of little theoretical details to know that it's correct, but in this case, it all works out. Here's a picture of a very easy tree for avoiding 1, 3, 2. Each one of these little squares, I'm not going to explain them, but these pictures represent sets of permutations. It's some representation for infinite sets of permutations. So this one has one disjoint union kind of rule, and it has one kind of Cartesian product style rule. Here's another example of a picture. These things tend to be very tall and skinny, so I just cut the picture in half and put it side by side. This is the top half of we call these things proof trees, by the way. This is the top half of the picture. This is the bottom half. But a lot of these are much bigger, and I can't really show them to you in a slide. They have size 50 or size 100 or even 1,000. But you can go to permpal.com and see some pictures there. Like we saw in a previous example, we have a lot of examples where a system of equations has a catalytic variable. So in order to do this, we had to track some kind of statistic on the permutations, and we get something like a y. And so there are equations where, like f of 2 is f of 3xy, but we substitute y equals 1. Or equations like this that will make anybody who's done this before think about the kernel method. And so with a system this small, I can solve this system with kernel method tricks and get an answer. But sometimes we have 200 equations, and the methods that I came up with using Grobner basis type stuff are just too slow with 200 equations. So every time I give this talk, I hope that somebody will know something about guessing and checking in a universe with one catalytic variable. And maybe this is the place where somebody will know something about that. But that's something we'd be really interested in. And lastly, we get plenty of things with 2 or more catalytic variables. If you have one catalytic variable, you're basically guaranteed your answer will be algebraic, but that goes out the window if you have 2 or more. So sometimes we get these weird equations where we're substituting 1 for y and y for z, or we're substituting y times z in place of y, or we have that kind of these funny substitutions. I don't know how to solve any of these. I don't think there's any hope. There are classes that are definite, or probably not definite, that get systems like this. So maybe there's a way to solve some of them. Maybe there's a way to do a guess and check and get a definite answer. Certainly, I would be very happy to hear about that. But I think sometimes you're just going to have messy systems and not be able to do anything about them.
But at any rate, it's a polynomial time algorithm.
Yes, it's a polynomial time algorithm. And in fact, we don't even use the equations. We just go straight from the specification to a polynomial time algorithm, which is even faster because we're not worried about all of this formalism of variables. Yeah, so we always have a polynomial time algorithm. The last pictures I'll show you, the last thing in the talk, is just some of the other domains that we've thought about. We've done these mostly by hand. This, again, I'm not going to be able to tell you what the pictures mean, but these funny square things, these represent sets of set partitions. So we can enumerate, these are set partitions in which every part has size 1 or 2. This is kind of like a not too hard exercise in combinatorics. We get a system of equations that actually has a derivative, which we can solve to get a differential equation for the ordinary generating function. So by hand, at least, this seems to work pretty nicely with set partitions. Polyominoes, Again, definitely not going to tell you what this picture means, but we can enumerate. This corresponds to Farrer's diagrams. So these are polyominoes that look like kind of a staircase aligned in one corner. We get a system of equations. This, in my opinion, is the interesting equation. T6 of xy equals T3 of x times y. And from this system, we can actually work out the generating function by hand. These are in bijection with integer partitions. So of course, that's the generating function that we get. And lastly, alternating sign matrices. So we were inspired by a paper by, I think, Linusson and a student, where they looked at alternating sign matrices that don't have a 1, 1, 1 anywhere in the matrix that look like this, like a lowest one, a highest one, followed by a middle one. And so we were able to kind of by hand work out some strategies that would find the generating function they found for those alternating sign matrices. Just to give you a little teaser, one thing that you might notice about this is it's not a specification. We've got two sets of rules, 1 and 2, with the same root. So what will be in a follow-up work is that sometimes you can actually do even better and get something that's not a specification, but a little bit looser, yet still determine all of the counting information that you want. We call these combinatorial forests because these are two trees. So two trees make a forest. And so we're going to explore that in future work as well. Sometimes you can do even better than a specification. So that's all I'm going to say for now. Please visit permpal.com if you want to see some pretty pictures, and I'm happy to answer any questions.
Well, thanks so much. We have 2 minutes for formal questions, and after that, people are welcome to stay for informal questions. Also, questions for Jay?
Hi, can you say something about how you control the combinatorial explosion when you're searching for the combinatorial specification among your rules?
Yeah, so this is a mix of things. One of them is designing strategies that don't go too crazy. And okay, well, what does that mean? That kind of just takes some practice. If you have strategies that are making very complicated, intricate sets, then you might end up in trouble. But another thing that we do is we're always looking for ways to identify when two different sets that we've made might secretly be the same set. So we're really using these representations, but sometimes you could have two different representations for the same set. So we have strategies whose only job is to take sets and try to simplify them in place, or try to identify when two sets have the same representation. So if you know that two sets have the same representation, you don't need to expand them separately anymore. We kind of link them together in what we call an equivalence node, and we only expand one of them. And so that's enough to save us a lot of the time. In practice, depending on the strategies we use, we'll go down to depth, maybe 7, 8, 9, sometimes 10 in this tree. So that's how far we can get before we're talking about hundreds of millions of rules and needing multiple days.
Cool, thank you.
Well, this ends the formal part of the talk. Robert, please stop recording, but people are welcome to stay for informal questions. For example,